Hi, this is Pat Johnson, your psychology instructor, and in this mini lecture, we're going to continue our discussion of memory, talking about the biology of memory and the concept of flashbulb memories. First, let's go inside the brain. Here's an image of the brain that you've seen from your textbook, and the part of the brain I want you to focus on right now is this structure right here. It's called the hippocampus, and this is an interior view of the brain, but the hippocampus winds around into the temporal lobe. So this big part of the hippocampus would actually be inside the temporal lobe. What the hippocampus does is it processes explicit memories and sends them on to various regions of the brain. So it's not where explicit long-term memories are stored. It processes explicit memories. It forms them into long-term memories and sends that information to different parts of the brain. And it's like hitting the save key on your computer when you're saving a document. That's what the hippocampus does. So let's go back to our three-stage model, our three-box model. Go to the second track with explicit memories and take a look at what the hippocampus is doing. So again, this is our second track right here, where we're dealing with explicit memories, and the hippocampus does this right here. It encodes memories from short-term memory to long-term memory. So right here is what the hippocampus does. So what we're going to look at is a famous case study of a gentleman who had his hippocampus removed. And I want you to look at this three-stage model and guess what his symptoms were. First of all, if you have no hippocampus or you have a severely damaged hippocampus, you can't do this. In other words, you are continually living in short-term memory. You can't form any new long-term memories. Here's the question, though. Could he pull information from long-term memory that was encoded before his hippocampus was damaged? And the answer is yes. He could retrieve. He could do this, but he couldn't form any new long-term memories. So there is a discussion of the famous case study HM in your textbook. You can find out more information about him on the internet. I'll also include a video in the optional videos where you can look at just this type of problem. So here's HM. He was a very famous case study showing what happens when a person has their hippocampus removed. In his case, it was a treatment for uncontrolled epilepsy. This was before there was a serious mapping of the brain done, knowing what the hippocampus did. So HM had uncontrolled epilepsy. They went in and removed that area of the brain, and after surgery it helped his epilepsy, but the horrendous symptom that he displayed was that he could no longer form new explicit long-term memories. And HM is famous because he led to the knowledge of what the hippocampus does. And unfortunately, we can see that same exact symptom in a syndrome called Korsakoff's disease or Korsakoff syndrome. And Korsakoff's is quite a common form of dementia where long-term alcohol abuse does severe damage to the hippocampus, and the person has the same symptoms as HM. In other words, they're living in the eternal present. So they can't form any new explicit memory. They are often perplexed when they look in a mirror and see themselves aging because they're living back in the time period when they still had a normal hippocampus. It's a very, very sad and debilitating disease. All right, let's go to our first track now where we're talking about implicit memories. And here we're going to a brain structure you're already familiar with, the cerebellum. Remember, the cerebellum is behind the brain stem. It's below the cerebrum. So here's the cerebellum. And we're also looking at the basal ganglia. And the basal ganglia is in here. And the basal ganglia and the cerebellum lay down implicit memories. And these are memories that are below conscious awareness. So they would be involuntary responses, things like classically conditioned behaviors, and muscle memory. Let me give you an example of an implicit memory that I had that was below the level of consciousness. I didn't know I knew this, but it came in really handy. A number of years ago, I needed to get a new car right away. My old car was getting dangerous. The repair place, the dealership, could not fix it, and they didn't want to give it back to me because it was so dangerous. And I was having a rental car and I needed a new car. So I went and test drove a car that was a stick shift, and I was really concerned because I hadn't driven a stick shift in probably 15 years, and I didn't know if I remembered how to work the clutch and the shifter. And what happened is, as soon as I got in the seat and looking at the pedals, I didn't even know which one was the clutch. But when I stopped looking at the pedals and just let my body take over, my basal ganglia and my cerebellum kicked in, and my body had that muscle memory, and I was shifting gears like a pro. So that shows you the difference between an implicit memory, an unconscious memory, and an explicit memory. What we know, we know. So if you've ever heard the adage that you'll never forget how to ride a bicycle, that's because that's basal ganglia and cerebellum. That's not hippocampus. That is below the level of conscious awareness. So here's what the basal ganglia and the cerebellum do. They do this automatic processing track of implicit memories below the level of consciousness. All right, let's talk about our last concept in this lecture, and we're going to talk about flashbulb memories. Flashbulb memories are memories that are formed when the brain responds to a really emotional event. And it's like the brain takes a picture and it goes slamming into long-term memory without effortful encoding. So if you're old enough, and some of my students aren't old enough now, but if you're old enough to remember 9/11, you probably remember where you were, who was around you, that type of thing, when you learned that the World Trade Centers were being blown up and the planes were going into them. And here's what flashbulb memory does, is it takes that event, and without much effort, you don't have to go back and forth and encode and retrieve and encode and retrieve. The adrenaline and the other stress hormones that are being given off during fight or flight take that long-term memory and slam it right into, take that situation and slam it into long-term memory. If you know anyone who is, let's say in their 60s or older, ask them where they were when John F. Kennedy was shot in 1963. And they will probably have just as vivid of a memory of that as people who are in their 20s or late teens and early 20s have of 9/11. So That's an example of just how strong and long-lasting a flashbulb memory is. And it's a survival mechanism. Our brain wants to be able to remember situations that cause that great amount of emotion, and because often they are dangerous. It doesn't have to be a horrible situation like 9/11. It could be something very wonderful. It could be something very happy like the birth of a child or the day you got married, but it's something that triggers very strong emotion. The last slide I want to show you is what's happening at the neural level for our brains when we're forming a new memory. And in this study, we have two rat cages. And this was the cage that just had rats with food and water. And this is showing what their neurons looked like. So it's a fairly simple neuron. It has dendrites, it has a cell body, it has an axon, it has axon terminals. But when they put the rats in a cage that was more like a little rat Head Start program where there were things to do and things to learn and activities, look at what happened with the neurons. It turns out that learning and memory is very good for your brain. If you are not a lifelong learner and a lifelong active person, meaning physically, aerobically active, your brain has no need to grow more complex. But if you are a lifelong learner and a lifelong aerobically active person, your brain continues to grow those neurons. So, how memory changes at the synaptic level. Synapses fire more easily. So if you've ever said to yourself, well, why do we have to learn this? I will never use algebra again in my life. This is stupid. This shouldn't be a requirement. If nothing else, think of that complex learning that is going on and the memory of the different stages of developing those skills for learning a subject matter. That is making your memory stronger, more durable, so that in the future, if there is ever something you do want to learn that is complex, you physically have more brain matter to do that. Neurons that are used grow more complex. I just said that. They not only fire more easily, they're growing more complex. And by this we mean their dendrites get more branches and there are more synapses. Receiving neurons grow new receptor sites. So learning and memory causes all sorts of good things to happen in your brain. Always be a lifelong learner.